So we're happy to have Omar Antolín Camarena from UNAM, Mexico City, and he will speak about higher generation of compact Lie groups by Abelian subgroups.
Thanks, Manuel, and thanks for the invitation. Let's get started right away. I'm going to tell you about a space that you can assign to any topological group that is called E2G. And this space, the way it's defined knows something about which pairs of elements of G commute and which pairs don't commute. And in particular, it'll follow directly from the definition that when G is abelian, E2G is contractible. Simon Gritschacher, Bernardo, and I, we proved a converse of this for compact Lie groups. If you have a compact Lie group and E2G is contractible, then G is abelian, but you don't need full contractibility. As long as pi1, pi2, and pi4 are 0, then G is abelian. And I like that theorem just because the hypothesis is kind of funny, pi1, pi2, and pi4. So in the case of discrete groups, there's an even better result due to Chihan Oke. If you have a discrete group and pi1 of E2G is 0, that's enough to conclude that G is abelian. And this is also related to a classic theorem of Araki, James, and Thomas that says that if you have a compact connected Lie group and the commutator map is null homotopic, then G is abelian. Having a null homotopic commutator map is called being homotopia abelian. So their theorem says that if you have a compact connected Lie group that is homotopia abelian, it's actually abelian. Okay, so I'll tell you first about the discrete case. And I want to mention a paper of Abels and Holtz that defines homotopy groups of a certain space and calls them being trivial, like higher generation. I'll explain these ideas. And then I'll give you a couple of proofs of Chihan's theorem that when pi1 of E2G is trivial, then G is abelian for a discrete group G. And then I'll tell you about the Lie group case. I'll explain how this space E2G is defined, and I'll describe a map that Simon, Bernardo, and I define that lets us prove this theorem. Okay, so first I'm going to be in the setting of discrete groups, and later on I'll use simplicial spaces, but for now I'm just going to use simplicial complexes. And when you have a family of subsets of a set X, there are several simplicial complexes that you can assign to that family. Maybe the most well-known one is called the nerve. The nerve of the family has vertices, the indexing set of the family. And then a simplex is a finite subset such that the corresponding sets have a non-empty intersection, right? Probably everybody's heard of the nerve and knows the nerve theorem, which I'll remind you of soon. Another complex you can assign to this family of subsets is the subset complex. There, the vertices are the elements of the set X, and you have a simplex if there is just one single subset in the family where all of the little x's belong, okay? So some points of X form a simplex if they are covered by a single element of this cover U. And you could also take the nerve of the poset given by the cover ordered by inclusion, and there, of course, the simplices are just chains of elements of the cover. And Abels and Holtz proved that the nerve of U and the subset complex of U are always homotopy equivalent, and also that if the cover is closed under non-empty intersections, and what that means is that whenever you have two elements of the cover whose intersection is non-empty, then that intersection is also in the cover, then the order complex of the poset is also homotopy equivalent to those two. And you can prove these things using the nerve theorem. Let me remind you what it says. If you have a cover of a space X such that for any finite non-empty subset of the cover, the intersection of those elements of the cover is either empty or contractible, in that case, X is homotopy equivalent to the nerve. That's the nerve theorem. I didn't give you the full hypothesis yet. There are several cases in which it holds. If you have an open cover of a space and X is paracompact, then this is true as written. Or if you have an open cover, and even if your space is not paracompact, you still get a weak homotopy equivalence. And if the cover is by nice subsets, for example, if X is a simplicial complex and the cover is by subcomplexes, then you don't need any further hypothesis. Okay, so using the nerve theorem, we can prove this theorem of Abels and Holtz that says that the nerve and the subset complex are always homotopy equivalent, and that additionally, if the cover is closed under non-empty intersections, the order complex is equivalent to those two as well. Okay, so for example, let's compare the nerve and the subset complex. So for every point in the space X, consider the set of indices of UJs in the cover that contain that X. Okay, so then the nerve of U consists of the finite non-empty subsets of a single JX, right? So the nerve of U is actually the subset. Sorry, what am I saying? Yeah, all finite non-empty subsets of JX are a simplex of the nerve. And if I take the subcomplex of the nerve formed by those subsets that all contain a fixed little x, then these subcomplexes form a cover of the nerve. And the intersection of finitely many of these n sub x's, that just consists of all indices for the cover, where the element of the cover contains x0 through xn. And so that intersection is empty if that set is empty, and it's contractible otherwise because it consists of, it's a simplicial complex where the simplices are all finite subsets of some fixed set, this set right here. Okay, so then the nerve theorem applies, and we get that the nerve of U is homotopy equivalent to the nerve of this cover, calligraphic n, and the nerve of that cover is exactly, by definition, the subset complex of the original cover U, right? Exactly, that's what I was saying in the beginning, that the subset complex of U, its vertices are the x's, and the set of x's forms a simplex if they're all contained in a single uj, and that's exactly what happens in the nerve of calligraphic n. And it's similar for the order complex of the cover. For a given element of the set, you can look at all of the elements of the cover that contain that one, and look at the order complex of just that part of the cover. Then these order complexes cover the order complex of the whole cover. And if you take the intersection of finitely many of them, well, you get the order complex of this subposet of the cover. The subposet consisting of all the UJs that contain all of the little x's. So the intersection is empty if that set is empty. And if it's not empty, and additionally you assume that U is closed under non-empty intersection, then this calligraphic I is a directed poset. And for a directed poset, the order complex is contractible. So in this case, the nerve theorem also applies, and you again get the result. Okay, so
Omar, so by order complex, you just mean the nerve of that poset?
Yes, basically okay. Yes, but technically, the nerve of the poset is a simplicial set,
right?
And
right.
the order complex is just a simplicial complex, but their geometric realizations are homotopy equivalent. So right. the exact definition of the order complex is that it's a simplicial complex, not a simplicial set, simplicial complex, whose simplices are the chains, the finite chains.
I see. Yeah.
But yeah, you should think of it as the nerve. It absolutely represents the same homotopy type. Okay. I'm just working completely in simplicial complexes for now. Just, I don't know, they're fun. Okay, so now I want to use these results of Abels and Holtz for groups, and I'll think of families of subgroups. Now, lots of naturally defined families of subgroups have a minimal or a maximal element, in which case the order complex is automatically contractible. So it turns out to be more interesting, instead of looking at posets of subgroups, taking some fixed class of subgroups, looking at all of the cosets for those subgroups, and then looking at the poset of cosets, okay? So here, F will be a family of subgroups of some discrete group G. And so that I don't have to make any distinctions, let's assume that it's closed under intersection, then all of these simplicial complex models will have the same homotopy type. And given this family of subgroups, I can form the family GF of all cosets of subgroups in the family F. And then you can apply any of those three constructions and you get three homotopy equivalent simplicial complexes. The nerve of the cosets, the subset complex of the cosets, and the order complex of the cosets. And so here's a description of each of them. The nerve, here the simplices are sets of cosets that have a non-empty intersection, right? That's sort of that, I mean, the corresponding thing with just the groups would not be interesting because groups always intersect and they always contain one, right? So going to cosets just makes these more interesting. The theorem we proved that shows the equivalence of these three models, of course, applies also for groups. It's just less interesting in that case. The subset complex of the cosets, there the vertices are elements of a group and the simplices are finite subsets that are contained in a single coset for some group in the family, okay? And then, well, the poset is there, the simplices are just chains of cosets ordered by inclusion, right? Now, if the family of groups happens to include G, then all of these are contractible. Maybe the easiest way to see that is that the poset here of cosets has a maximal element. Right? But it's actually not hard. Even if you didn't know that these three are homotopy equivalent, it's not hard to show that if the family F includes G, then all three of them are contractible. All right, so what's this higher generation idea of Abels and Holtz? If you take a family of subgroups of some discrete group G, assume again that it's closed under intersection, then you can take the colimit of the entire family. This is the colimit of a diagram of groups whose shape is the poset F ordered by inclusion, right? And here's a nice, easy presentation for it. It has generators for each element of the union of the family of subgroups. This union is some subset of G, not a group or anything. It has a generator for each element there, and it has a relation that says, if you find two generators that happen to belong to a single group in the family, then you can multiply them the way they're multiplied in the group G, okay? So that's what these generators and relations say. Multiplications are the same as long as they are between elements that come from a single group in the family. And there's a canonical homomorphism from this colimit to G given by sending the generator for G to G itself, right? That respects this relation, obviously. Okay, so Abels and Holtz showed, and this is not hard to show, that pi zero of the nerve of the cosets for the family of groups F, that is given by G mod the subgroup generated by the union, okay? And that pi one of the nerve is given by the kernel of this canonical homomorphism, okay? So in particular, if pi naught is trivial, that means that the subgroups in the family F jointly generate G, right? So Abels and Holtz call the family N generating if the nerve of the cosets of groups in F is N connected. Sorry, N minus one connected. Yes, what it says here on the slide, N minus one connected. Okay, all right, so in particular, I want to apply this to the family of abelian subgroups, right? So take the family of abelian subgroups and you have these three simplicial complexes that are homotopy equivalent. The nerve of the cover by cosets of abelian subgroups, I'll call those abelian cosets. Okay, so abelian coset just means coset of some abelian subgroup. So you have the nerve of the cover given by abelian cosets. You have the subset complex. So here, the simplex, so for this one, the vertices are elements of the group and a bunch of them form a simplex if there is a single abelian coset they all belong to, And so Chihan proved that if these spaces are simply connected, then G is abelian. Okay, so here's one way to prove that. By Abelson-Holtz's theorem, you have this group. Remember that this is the presentation I gave you of the colimit of the family of abelian subgroups. Right? So the colimit says you have generators for all the group elements. You're allowed to multiply them the way you normally do in the group when they commute. And so remember that pi1 was the kernel of the canonical homomorphism kappa. So if pi1 is trivial, that means that this canonical homomorphism gives us an isomorphism between the colimit and G. Now, when G and H commute, then for restricted to commuting pairs, the inverse map is a homomorphism, right? So this means that on H, the formula sending the generator G to its inverse gives you an endomorphism. And since H is isomorphic to G, that means, and this endomorphism corresponds to the inverse map, that means that the inverse map is also an endomorphism of G, and therefore G is abelian. And this is basically Chihan's proof of this theorem. I think he does not cite Abelson-Holtz's theorem, but he proves a similar result anyway. And this part of the argument is definitely in Chihan's paper. Okay, so now let me give you a slightly different description of the subset complex of the cover of abelian cosets, right? So remember that the simplices were subsets that are contained in some fixed abelian coset, in some single abelian coset. That's equivalent to saying that if I multiply all of the elements by G0 inverse, the results commute pairwise. And if these commute pairwise, then just all of the quotients commute pairwise, right? Because every quotient here is a product of some of the quotients obtained in the line above, right? Well, is in the group generated by the quotients in the line above. So just to give this a name, we'll say that a subset of elements that satisfies any of these equivalent conditions is affinely commutative. The idea is that, well, it's not commutative, but if you translate it so that one of the elements is at the origin, then you get a commutative set, right? So it's the same difference as between vector spaces and affine linear subspaces. So we'll call this subset complex the affine commutativity complex. Just notice that any set that has only one or two elements is affinely commutative. For a set with two elements, here in this line, you only need to check that one thing commutes, and one thing always commutes. And then if you have three or more elements, that's affinely commutative, if and only if all the three element subsets are affinely commutative. This corresponds to the fact that in a group, a bunch of elements generate an abelian subgroup only if every pair of them commutes, right? Okay, so let me remind you of a nice formula for the fundamental group of a simplicial complex. So take a connected simplicial complex, and then take its one skeleton is a graph. Take a spanning tree of that graph, and there's a very well-known presentation for the fundamental group that has basically one generator for every edge outside the spanning tree, and the triangles in X give you the relations. I'll be a little redundant and throw in some extra generators just to simplify the presentation. So take a generator for every edge of the simplicial complex, including the tree edges. But then some of them are trivial, like if your edge was actually a single vertex, then it's trivial. The generator for an edge is the inverse of the generator for the edge in the opposite orientation. The tree edges have trivial generators, and that lets me write the last relation without any special cases. Whenever you have that UVW form a simplex in X, then XUV times XVW is XUW. So just to be absolutely clear, remember what loop each of these things corresponds to. Pick a base point in X, and then the generator XUV of the fundamental group corresponds to the following thing. You start at the base point, you move along the spanning tree to the vertex U. There is a unique path in the spanning tree that gets you to the vertex U. Then you go across the UV edge, and then you go back to the base point along the spanning tree again. And you can easily see that these relations hold true for those loops. All of the parts on the spanning tree just cancel. Okay, so if you apply this to the complex of affine commutativity, then you get this nice presentation for its fundamental group, which is different from the description of the fundamental group as the kernel of the canonical homomorphism that we had before, right? So that was a description as a kernel. That means a description by equations. And this is instead a description by generators and relations, okay? So it has generators. So I can pick a spanning tree. I'll just pick the star centered at the identity element of G, right? So the spanning tree I'm picking has all the edges that go from one to some other group element. So we get generators for every pair of elements. Remember that the one skeleton is the complete graph. And the generators that have a 1 in them are trivial, and they multiply in the co-cycle way. GH times HK is GK whenever that triple is affinely commutative. All right, so there's this little calculation that I don't know, it's at the same time trivial and a little bit surprising. If you have a triple that's affinely commutative, the commutators behave the same way as the generators did on the previous slide. The commutator of G and H times the commutator of H and K is the commutator of G and K. It's trivial to prove. You just have to commute these two quotients. And but this is definitely not normally what commutators do. They do this exactly when the triple is affinely commutative, right? This is obviously an if and only if, and this proves both directions. But knowing that they multiply this way, I can define a homomorphism from the fundamental group of the complex of affinely commutative sets to the commutator of G, just sending each generator to its commutator. And this proves that the relations are satisfied. And this homomorphism is obviously surjective because the image includes all of the generators of the commutator group, right? The commutator group is generated by the commutators. So since this map C has to be surjective, if the commutator is non-trivial, then the fundamental group of the complex of affinely commuting sets can't be trivial either. It needs to surject onto this non-trivial group. So this gives you another proof of Chihan's theorem. If the subset complex of this cover by abelian cosets is simply connected, then G is abelian. And the proof for the Lie group case that I'm going to explain generalizes this proof rather than Chihan's original proof. Okay, so what do you do in the Lie group case? More generally, you take a topological group. I'm going to define a space now, which is an analog that takes the topology into account of this complex of affine commutativity that we were working with before. So it's easy. It's a simplicial subspace of one of the usual simplicial models of EG. In EG, the n simplices are G to the m plus 1. And here I'm taking the subspace where those m plus 1 elements are affinely commutative. So this is a subspace of, there's sort of like two isomorphic models of EG that people use. I'm talking about the one where face maps delete coordinates and degeneracies duplicate coordinates, okay? So this is a simplicial space there, and its geometric realization is the space E2G. The two might look a little funny. It's because this is part of an infinite family of spaces where this is some natural number, EQG. And EQG is similar to E2G, but instead of having to do with commutativity, it has to do with nilpotent groups of class at most Q. Or maybe I'm off by one. 2 should correspond to, yeah, I guess abelian groups are nilpotent of class 1. So then EQG is analogous to this, but instead of abelian subgroups, it has to do with nilpotent subgroups of nilpotency class at most Q minus 1. Okay. The original definition of this space was more like the other common model of EG. It was defined by Alejandro Adem, Fred Cohen, and Enrique Torres Giese in 2007, I believe. And so they had a space of n simplices, G cross the space of commuting n tuples in G, which I can write as homomorphisms from Z to the n into G. These two are isomorphic in the usual way. If I have a tuple like this, then I can keep G0 for this element of G, and then just take quotients of consecutive elements to get a commuting n tuple. And in the other direction, what I do is if I start with something here, which is a group element followed by n commuting group elements, I just take partial products, and then I get an affinely commuting set. Okay.
Omar, can I ask a question?
Sure.
Yeah. So how are these EQGs related to EG altogether? The EQG.
They're all simplicial subspaces of EG, and they form an increasing sequence of subspaces of EG. They do not exhaust EG. They don't exhaust EG because G typically has lots of subgroups that are not nilpotent, right?
Right. So is the co-limit of all of these somehow related to the Malsev completion of G or something?
I think it should be, but honestly, I don't think anybody has worked much with the co-limit yet. The one thing, I think the one remark about the co-limit that I can point to that has been published is just what I said now, that it does not exhaust G, and that you shouldn't expect it to, because G has lots of finitely generated subgroups that are not nilpotent typically. If every finitely generated subgroup of G were nilpotent, then these would exhaust G.
I see. Okay.
Yeah, but I don't think much has been done with the union of them yet. In fact, I think most of the work on this whole family of spaces is centered on E2G still. The other ones have been less explored. Bernardo and Simon have a nice paper out now on E3G. And Bernardo and I computed the EQGs specifically for SU2. And they're actually, all of them, starting with E3, are rationally equivalent. So SU2 just does not have a large variety of nilpotent subgroups. It turns out that all of the nilpotent subgroups of SU2, which are not abelian, are finite and are conjugate to a standard embedding of the generalized quaternion group of order some power of 2. So not just rationally equivalent, but as soon as you invert 2, all of the EQ SU2s are equivalent to each other. Okay, so what is known about these spaces? The answer is really that not much is known. One thing that's obvious is that if G is abelian, then this thing is all of EG, which is contractible. If G is discrete, then it's not hard to show that this space I described, even though it's infinite dimensional and so on, it's homotopy equivalent to this complex of affine commutativity of G that we described at the beginning. It's sort of the same relation between, sorry, I just want to point out that this E2G, it's like EG. It always turns out to be infinite dimensional, except if G is trivial. But it is homotopy equivalent to that simplicial complex I showed you, which is actually a finite simplicial complex in case G is finite. And the case of general topological groups, I don't think has been studied very much. Most of the work has been focused on compact Lie groups. There are good reasons for this. Well, it's probably the most interesting case, but specifically for the compactness, say you're interested already in the Lie group case, why would you focus on compact ones? Well, often, but not always, E2G is homotopy equivalent to E2 of the maximal compact subgroup. There's a theorem by Alexandra Petit and Juan Soto that says that if G is the complex points of a reductive algebraic group, or is the real points of what's called a real reductive algebraic group, then E2G does not change homotopy type if you replace G with its maximal compact. So, and this includes UN, SUN. So a lot of these, a lot of the time it makes sense to focus on the compact ones and you're not really missing much, but it's definitely, this space is definitely not invariant under passage to the maximal compact subgroup in general for Lie groups. For example, for the Heisenberg group, the 3x3 upper triangular matrices with real entries, one's on the diagonal, and where like the corner is taken in R mod Z, that one is not, E2 of that thing is not homotopy equivalent to E2 of its maximal compact, which is just a circle. Okay, so, but often it makes sense to focus on compact Lie groups. And there's also a variant of this space. I define this E2G as the geometric realization of some simplicial space. There is a simplicial subspace of that where in each degree, you only take the connected component of the tuple of ones. And that space is a little bit more tractable for rational cohomology calculations. Alejandro Adem and Juan Manuel Gomez proved that if you have a compact connected Lie group, then this variant, E2G1, formed by realizing the connected components of the base point, that has the homotopy type of a CW complex with finitely many cells, and its rational cohomology it has a description that is similar in flavor to the classical descriptions of rational cohomology of BG and other spaces associated to G. So it's the cohomology of G mod T squared. On the cohomology of G mod T, the Weil group W acts. T is, as usual, the maximum torus. And so you take the fixed points for the diagonal action on this product.
Omar, I missed what the one means. Sorry.
Right. So the one means in these spaces, take the connected component of the sequence of all ones.
Oh, I see. I see.
That is a simplicial subspace of this one.
I see.
Mm-hmm.
Okay.
We call it the one component of E2G, but that's a bad name because E2G itself is connected. What's not connected is the space of n simplices for all n, and you're taking the component of the sequence 1111 in that space of n simplices. So I've tried to stop calling it the one component since this E2G is already connected.
I see.
Okay. So are there concrete calculations of the homotopy type of E2G? And there are very few of them. Chihan Oke did some computations for discrete groups G. And so for example, he proved that if you take an extra special group, I'll specifically focus on order 32, but he proves something for all extra special groups. So these are particular groups of a prime power order. There are two of them of order 32. If G is either one of those two, then its fundamental group is Z mod 2, and its universal cover is homotopy equivalent to a wedge of 151 copies of S2. So of course, this tells you right away that pi 2 is Z to the 151, and then you could use the Hilton-Milner theorem to compute other homotopy groups if you want. For example, pi 3 works out to be Z to the 11,476. In his PhD thesis, Simon proved that E2 of the infinite unitary group is homotopy equivalent to this product. It's the product of all the connective covers of BU. The BU brackets 2n is the 2n minus 1 connected cover of BU. And so instead of Bott periodicity, you have Bott linear growth, right? Pi 2 of E2 of the infinite unitary group is Z to the n minus 1. So these don't repeat periodically, they grow linearly. And Simon, Bernardo, and I did some computations for O2 and SU2, and I really like these results because the answers are very simple and just seem completely random. E2 of O2 is homotopy equivalent to S3 wedge S2 wedge S2. And my favorite is that E2 of SU2 is homotopy equivalent to S4 wedge the fourth suspension of RP2. This lets you calculate homotopy groups if you want. For example, pi 10 of E2 SU2 turns out to be Z mod 4 times Z24 squared. And pi 10 of E2 O2, well, that's big because we have 3 legends here. Hilton Milner tells you it's this horrible looking group. I have to admit, I don't, this slide is like, I mean, the results of what's interesting here are these results. I include the homotopy groups because I sometimes give this talk to a more general audience, and topologists know that once you know something like this, you can easily compute the homotopy groups using the Hilton-Milner theorem, but not everybody knows that. So it's just, to bring home the fact that we can really compute things. This calculation here in particular, that it has that homotopy type, that's I really like that computation. It works in a weird way. It is the result of a series of small miracles. It's completely ad hoc. I have no idea how to generalize this to other groups. So far, what we do to compute the homotopy type of an E2G is get very detailed knowledge of all of the abelian subgroups of G and how they intersect. And then, just hope for the best. This required first computing its cohomology ring, and then, well, I don't know, it's a series of coincidences that is hard to reproduce for other groups. Okay, so now let me describe the commutator map. If you remember, I gave you 2 proofs of Chi-Han-Okei's theorem for the discrete case that says that if pi 1 of E2G is 0, then G is abelian. And the second proof used a homomorphism from the fundamental group of E2G to the commutator group. So here's a space level version of that map. One reason I like our definition of E2G, which is isomorphic to the original definition, but a little different, is that in this isomorphic version, the following map is just evident and suggests itself. I don't think we would have ever thought to look at this map in the other isomorphic model, okay? But so what you can do is define this simplicial map. You take an affinely commuting n+1 tuple to the n tuple of adjacent commutators, the commutators of adjacent pairs. Now, this in general is not the kind of thing you would expect to be a simplicial map. Here on the left side, face maps remove elements, and on the right side, face maps multiply adjacent elements. But the affine commutativity condition is exactly what tells you that those 2 operations do correspond to each other, and you get a simplicial map. That's that little lemma I showed you earlier. Okay, so the geometric realization of this map is what we call the commutator map. And in the case when G is discrete, the homomorphism it induces on pi 1 is the homomorphism I already told you about. The existence of this commutator map is a bit of a miracle. I already mentioned this family of spaces EQG. And when Q is bigger than 2, I don't know how to define something analogous to this commutator map. And I don't think anyone does either. So it's I don't know, it's special for abelian groups. I mean, not for when G is abelian, for when you're talking about abelian subgroups of G, not nilpotent subgroups of G. Okay, so what our main theorem says is that the following conditions are equivalent for compact Lie groups. It's equivalent that G is abelian, that E2G is contractible, that the commutator map is null homotopic. This is the analog of the statement in the discrete case that it would be equivalent to say that that homomorphism C is 0. Since we know it's surjective, if it's 0, that means that the target is 0, and then G is abelian. Right? So this is how it generalizes to space level. And those conditions are also equivalent to this one, which is maybe the most interesting, that this space has trivial pi 1, pi 2, and pi 4. Okay. So let me tell you a bit about how this is proved. So let me mention those homotopia abelian groups again. In the case of compact connected Lie groups, our theorem implies that if C is null homotopic, then G is abelian. But in the case of compact connected Lie groups, if they're connected, this is a much easier fact that you can deduce from a classic theorem of Araki, James, and Thomas. So what they proved is that if you have a compact connected Lie group and the algebraic commutator map, I just call it algebraic to distinguish it from the map I called commutator map on the previous slide. This is just the commutator as a map from G cross G to G. If that is null homotopic, then G is a torus. And it's very important that the compact Lie group here is connected. Also, let me point out that the proof of this theorem of Araki, James, and Thomas relies on the classification of Lie groups. The paper where this theorem is proved is pretty short, but it only proves like the last remaining case of the simple Lie groups. And their theorem really requires connectedness. It's false for disconnected groups. A simple example is the following. Take S1 cross the quaternion group Q8 and mod out by the diagonal subgroup generated by -1, -1. That quotient is homotopia abelian, but it's not abelian. The elements that are in the commutator are 1, 1, and 1, -1. And this means that the commutator, and since these elements can also be written as with the minus sign on the other side, the commutator is contained in the image of S1 cross 1. So and the image of that thing is just a smaller S1. So the commutator is contained in a path connected subgroup, and that means that the commutator map is null homotopic in this example, right? Because its image is just 2 points, and you just have to move each of those 2 points to the base point. So this one is homotopia abelian, but it's not abelian. And okay, so let me explain how you prove that if the commutator map is null homotopic, then G is abelian. And in particular, this argument on its own already proves our theorem in the case of connected Lie groups. So in the case of connected Lie groups, our theorem really is just a pretty direct consequence of the Araki, James, and Thomas theorem. And what's interesting is the extension to disconnected compact Lie groups. Okay, so how do you prove this implication? Well, if you have a simplicial space, you could just take the geometric realization of the skeleton, of the nth skeleton, and if you call that Fn of the geometric realization, that filtered part, then you get this operation is natural, so you get a commuting square like this, and the realizations of the one skeleton of both of these spaces are easy. For the classifying space of a group, the one skeleton is just the suspension of the group, right? It has there's a unique zero simplex, and then the one simplices are G. And so both of the face maps are just the map from G to a point. The colimit of that is the suspension. On the other hand, what do you get for the one skeleton of E2G? Well, remember that any pair of elements is affinely commutative. So if you're only looking at 0 and 1 simplices, E2G is still the same as EG. The difference comes in when you look at triples, which is 2 simplices, right? So for 1 simplices, this is the same as EG still. And the 1 simplices are G cross G. The 0 simplices are G. And the projection maps, the face maps are the 2 projections from G cross G to G. So the push out of that is G join G, which here I've written in a homotopy equivalent way as the suspension of G smash G, right? And if you look at the definition of the commutator map, it follows, and it makes sense, that the horizontal composite across the top is just the suspension of the map given by commutators. Notice that the commutator map descends to the wedge because if either of the entries in a commutator is 1, then the commutator is 1. So it's well defined on the wedge. Okay, so if C is null homotopic, then this composite here going down to B of the commutator is also null. And so then its adjunct is null and the commutator factors through this smash product. So then the commutator is null homotopic, which by definition means that the group is homotopia abelian. And then if you know that G is connected, you deduce that it's a torus, right? So this is the proof in the case where you can just apply the Iraqi-James-Thomas because you're assuming that the group is connected. I should have written that up here. Okay, so what do you do to extend this theorem to other cases? Let me just prove the most interesting part now that I've explained roughly how this goes. Let's assume that pi1, pi2, and pi4 of E2G are 0 and show that C is null homotopic. Okay, so the first thing you do is you look at the case of SU2, and by hand you prove that loops of the commutator map has a section up to homotopy. Then the next step is that you show that if pi4 of E2G is 0, then the identity component of G is a torus. So then you have, in this case, you'll have an extension of pi naught of G by a torus, right? That's what G would be. And finally, if you already know that the identity component is a torus, and you additionally assume that E2G is 2 connected, then you can show that the commutator map is null homotopic. And this is easy because if the identity component is a torus, then the commutator subgroup is also a torus. And maps like this, like the commutator map, are just given by H upper 2 with coefficients in Z to the R, where R is the rank of the torus. And so if we're assuming that E2G is 2 connected, that's automatically 0. So this map is null homotopic. The interesting part is this middle step. If you assume that pi4 of this is 0, then we have to show that the identity component of G is a torus. Okay, so this is what we want to prove. Okay, so look at the identity component of the commutator group instead. That's a compact connected Lie group, and therefore its universal cover is a product of maybe some R to the M and several simply connected simple Lie groups. And we want to show that there are actually no simply connected simple Lie group factors, that the universal cover is just R to the M. If you had some factor Ki, it's known that there's always a homomorphism from SU2 that induces an isomorphism on pi3. So as long as you have one factor Ki, you can find a homomorphism from SU2 to this identity component of the commutator group where its effect on pi3 is injective. Okay, and then using the section I mentioned earlier, you can factor this pi3 of this homomorphism, which here I've changed the codomain to land in all of the commutator group instead of just the identity component. That composition of pi3 of F with the inclusion, you can factor that through pi3 of some map from loops E2 SU2 to loops E2G. And this one we're assuming is 0, because if we assume that pi4 of E2G is 0. So then as a conclusion, we get that this map that was injective is also 0, and this means that there was no factor Ki. And so this thing was a torus. And the identity component of G is a subgroup of that, so it's also a torus. Okay, so that's a quick sketch of how this is proved. Thank you very much. I think I ended a little bit early.
So let's thank Omar. Are there any questions or comments?
Can you? Oh, sorry, go ahead.
Oh, go ahead, Paul.
Can you say more about this fact that there's a map from SU2 to any simply connected non-abelian Lie group that induces an isomorphism on pi3?
It's a simply connected simple Lie group.
Sorry, simple. Yeah.
Yeah, I think again it's proved. Unfortunately, I don't feel certain I know how it's proved, but I think again it's using the classification, and you just prove that in all of the cases you find an SU2. It depends on the classification. Pretty sure. And I mean, it's not surprising if you think of any simply connected simple Lie group that you're like familiar with. It clearly has an SU2 subgroup.
Mm-hmm.
So the trick is knowing that pi3 of those is always Z.
Yeah.
And, but so this is just a strengthening of that. It's not just that pi3 is Z for simply connected simple Lie groups, but in fact, it's a copy of Z that's generated by some subgroup SU2. And again, I think it's done case by case.
Cool.
I had a question along the same lines, I guess. So am I right that any semi-simple Lie group has a copy of SU2 or SO3?
Yes, I think that's right. Yeah.
But now it seems that you're saying that any simple one has a copy of SU2 inside it.
A simply connected simple one.
Yeah, that homomorphism that you said is injective.
I think so, but it's only for simply connected simple Lie groups.
Oh, I see.
So, for example, I'm not claiming that SO3 has a copy of SU2 inside it.
Right. I see.
Yeah, here this factorization was applied to the universal cover of the identity component of the commutator.
So can this fact be used to say anything about I don't know, E2G, where G is simply connected simple Lie group?
Yeah, maybe in that case you can get away with less. Let me see. Yeah, so I think if G is simply connected, then yeah, it's probably true in that case that E2G is already 2 connected. So what that would tell you is that for a simply connected simple Lie group, yeah, I'm not absolutely certain this is correct right now, but I think what you get is that for a simply connected compact simple Lie group, as long as pi4 of E2G is 0, then the group, pi4 is not 0. Pi4 cannot be 0. If it were, then the group would have been abelian.
I see, thanks.
Yeah.
Omar, I have a question. It's more of a general question. So, I mean, there are algebraic constructions for EG and BG that work for any algebra, right? The bar construction of an algebra.
Right.
And there's also a version for E. So, I mean, I've heard you speak about this a few times, but I've always wondered if there's an algebraic version of this E2G that can be applied to more general objects. And then what would that measure? Yeah.
Yeah,
I mean,
kind
not
of
sure.
Like we have talked about this in the past, and
right.
It seems like maybe you could adapt just this definition where you take the. Yeah, I'm not sure. You can certainly adapt this to algebras by looking at like sort of a subcomplex where spanned by tensor monomials of commuting elements. I think that probably works, but I'm pretty sure nobody's seriously looked at it, and I don't think we really know anything about what would result from that. But it might be interesting. Yeah. I have not thought about it.
Yeah, I mean, I'm always working with algebras which are commutative up to homotopy and trying to obtain partial information from them, you know?
Right.
So, yeah. Any other questions or comments? If not, we can thank Omar again.